if you go to the slide, the summary slide, Sergio, please. Oh, let's first of all, let's go on show who participated in our session, and then we go to the summary. So we had 5 participants in our session. So we had Juan Sebastián Zambrano from Universidad de Cuenca in Ecuador, Professor Julio Ramirez from Purdue University, Maha Kenawi from University of Nevada at Reno. She's a postdoctoral fellow there. Anthony Trogovich, who is a former student here at UC San Diego and is a lead structural engineer, John A. Martin and Associates in the Bay Area, and Govardhan Bhatt of the National Institute of Technology at Raipur. So we had an excellent session with most participants giving input to their research needs. And following the recommendation, we look at 3 potential topics. One is into the shear strength of core walls in tall buildings. The second one on backstay diaphragms. And the third one on the use of high strength reinforcing steel as in lateral force resisting systems as longitudinal reinforcement. So if we go to the summary, thank you, Sergio. So in what happens, to give you a little bit of background information to you all, with the advent of tall buildings in the West Coast of United States, in particular Seattle, Bay Area, and Los Angeles, and even here in San Diego, we see that structural walls in the way of core walls or just isolated walls in these buildings are making use of high strength concrete, 10,000 PSI or so. And they're taking, to minimize the section, they're taking these walls to the maximum shear stresses that are allowed by the ACI code. Now, the provisions of the ACI code were not developed for these walls of this size. These were developed mainly for thin webs of I-beams or so. And we have been using those here to basically limit the amount of shear stresses these walls can take. Now, we don't have a lot of knowledge on if this is applicable or not. We have no knowledge if we have size effects, and we don't have sufficient computational models to look into this problem. So this basically offers a unique research possibility of using the shaking table as to basically do a capstone design project. And this is no different from the projects I work in the diaphragm seismic design methodology, and similar to what John and his collaborators are doing with the tall wood building project, where we do a series of tests, build up the computational models to a significant level of understanding, and then go and do a final capstone project. So since we're working here in these core walls in buildings with very large sizes, it's impossible to test this at full scale. But certainly in different universities, we could test a number of core walls with different geometries and so on as part of a collaborative effort, calibrate different tools of different detailing finite elements, and then come and do a capstone here. I think by talking to Julio Ramirez, Professor Ramirez, these large research programs can be, for example, taken from NSF or NIST or both, and using the science plans that are in NERI as collaborative programs. The second topic is on backstay diaphragms. And for those of you, it's a very specific name or so. So you have a tall building, let's say 20, 30, 50-story building anywhere on the West Coast. And then those buildings are not just a single tower. And in the lower floors, they spread out like a podium. And in many cases, they actually go on the ground 3, 4, 6, or 8 levels as well. So now when you have the inertia forces coming from the tower and into this podium, they disperse and they look to a lot of these inertia forces get into the retaining walls or to the walls that the architect has placed in this building. So this looks like a very elementary problem, but in practice, many structural engineers use black boxes, upper and lower bounds, but they don't even know if this is an upper or lower bound. So we know very little about this. It's again, these are extremely large size elements, and they lend themselves to do some scale testing on the on the base frame that Professor Conte mentioned, so we can expand out of the platen as a capstone project of several studies that will extensively use computational simulations. Again, following the framework and the model that of the Niels Stolwood program, or the DSDM programs in which I worked in the second one, I think this could be a very successful venture as part of a collaborative effort. These are large programs, of course. The final one is topic 3, is that now the trend, ACI has enabled now to use high strength reinforcing steel, which is grade 80 and grade 100, and for particularly grade 180 for the lateral force resisting systems in core walls and structural walls in buildings. And the aim of this is basically to reduce that significant congestion we have in these walls. Sometimes it gets very, very congested in buildings in either Los Angeles, San Francisco, in the Bay Area, or in Seattle. So the idea is to use these higher strength reinforcing steel to reduce congestion. But the thing is that we don't know much about the dynamic behavior of this reinforcing steel. They come at higher strength but reduce ductility. So it will be great to again go from the bar in air testing to component testing and end up with a capstone project on the LH Post 6, where we are able to test at some kind of a scale buildings and compare or try to get some information about grade 100 reinforcing steel. Sometimes it even greater. I know Anthony Drogovic mentioned that in some cases they use grade 150, but no for longitudinal reinforcement. But there is a lot of interest in the community to implementing higher grade reinforcing steel. So those are the basic 3 topics that we discuss in our group. And I would like to pass it to our second subgroup that look into another topic.
Yes, thank you very much, Jose. So Jim Malley now will summarize for his group.
How do I share? Let's see. Let's see. Trying to figure out how to share my video. Oh, there it is. I'm sorry, I lost it there for a second. Let's go there. Okay, can you see it all right?
Yes.
Okay, great. So the steel building structures topic. I'm going to try and start my stopwatch and stop at 3 minutes. And so the next is the group. The participants, myself and Emin Prit Singh from UCSD, did a great job as our scribe. Hernan Castaneda, PhD student at UMass. Devin Huber from AISC, the director of research there. Jakob Valagura from KPFF in San Francisco, design engineer. Barb Simpson, assistant professor at Oregon State, and Paul Richards from Durfuse. And we also had a very good conversation. So So we had 3 topics. The first are what I'm calling BSSC rocking systems. This came out of the BSSC research study that Bill Holmes talked about this morning, and it was the one primary steel topic in the document based on some work done by ATC 116. What we find is that many standard code type shorter buildings, brace frames especially, will actually rock rather than before they actually buckle braces or yield the BRBs, and if they're on spread footing foundations. So it would be helpful to know how those systems are actually going to behave, what the interaction would be with the rest of the building, etc. And then you could also design some intentionally rocking systems. There are other countries that have provisions for rocking designs that we could compare and contrast with our standard systems. We thought about doing fixed base test, and then a rocking base test, just allowing it to bounce on the table, and then potentially even using the soil box and getting soil structure interaction. So that was the first thought. The second is steel wood systems in combination. Thought maybe John Vanderlint and the group would be interested in this because it seems to be fairly popular to try and combine steel lateral systems with some of the CLT gravity systems. And a lot of the interactions with diaphragms and how those are all going to work would seemingly be a very interesting test to have done on the table. Really could incorporate some of the resilience concepts as well into that topic. And then our final one is a little more open. We didn't kind of get too detailed on this one, but the idea was to look at a main shock on a system, whether it be an older system, not a complying system, and also complying system, so we could have two prongs in the program, and then do some damage assessment after the first test to decide how you might want to repair it or not repair it. Maybe if you didn't think you needed to repair it, do an aftershock test to see what happened there, and then potentially repair it, and then maybe do the original shock to sort of kind of put the specimen through its paces. And really there's not very much information on kind of post-earthquake response to aftershocks, as well as repaired and then retesting. So that would be the third topic that we thought about. So with that, I think I'll turn it over to the next presentation.
Yes, thank you very much, Jim. Number 3 will be John Vanderlint on timber wood frame building structures.
All right, let me. Okay, hopefully you guys can see that. We're going to do a group presentation here, so we'll each hit one bullet. And so with that, we also want to just acknowledge our scribe, our participants. We were a smaller group, so it was myself, Larry, and Steve. And with that, let's see, I think we said, Larry, you'd be first, and then Steve, and then me.
Right. Yeah, thanks, John. I also just wanted to say it's a real honor for me to be able to participate in this workshop. And I always enjoy working with the researchers at UCSD. So our first idea for wood had to do with developing a research program to look at inexpensive response modification devices that may be dampers or base isolation, something that would serve to improve performance, reduce damage. And looking at that second bullet first, being able to utilize the vertical component, or look at the vertical component with the changes on the table might be very useful based on previous base isolation research and things. And then also we talked about simplifying the code provisions that exist right now that are kind of a barrier to implement this sort of response modification into light frame wood construction. So research is always good for moving things forward. So with that, I will hand it off to Steve.
Thanks, Larry. Thanks, John. And good morning or good afternoon to everybody who's here. The second bullet point was really derived from another research opportunity that Bill Holmes mentioned this morning. And that was as part of the ATC 116 project that we were involved in. We've taken a really hard look at short period structures and what affects their collapse resistance and their performance. And for light frame wood, it was very apparent that one of the key performance indicators is just really brute strength of the structure, kind of a ratio of peak capacity to building weight. And so more research needs to be done there to try and develop some, I think, simplified provisions for wood buildings that can take kind of a larger holistic look at their entire performance to come up with better performing structures that really don't have to cost much more than they do now, and to get those building code provisions developed that would support that. And with that, I'll turn it over to John.
All right, thanks, Steve. And Jim, I'll just add, we did actually have some discussion on the wood-steel combination, kind of right up that alley. So I think we all love the topic. We don't have it down here, but I'm glad you did. So functional recovery of wood buildings. I think this is, obviously this is a huge topic with the ongoing work with NIST and others, but and I think there's a lot of NSF projects that are focusing on this. And so it's really finding that balance between the structural and non-structural components and how those can, in a way, people focus and they look at a single component or a couple of components, but how do you get them all working in concert is kind of the thought process here. And then, really, and this is maybe more overarching, it's really that motivation for actually doing it. But that's, how do you determine what the building performance should be to achieve certain goals or objectives at the community level? So it's really almost like in a sense, it's a de-aggregation, except that we can't do it that way. So we'll do it forward and we'll just iterate. And so I think that's in a way critical. And then we, just for opportunities, I'll just close by saying that, as Steve kind of indicated, we thought we'll just add one bullet here, but really most of the collaboration comes from the development of commodity and proprietary products of both. And these all require industry and academic collaboration throughout. So we see industry as being a key participant in all these project teams that are related to wood. And with that, that is our summary. So let me stop sharing and pass to group 4.
Thank you very much, John. Group 4, Georgios Tsampras on seismic retrofitting of building structures.
Yep. Let's see. Okay, can you see my screen?
Yep.
Perfect. Okay, so our group consisted of Leo Panian from Tipping Structural Engineers, myself, Professor Benson Singh from UC San Diego, Alex Lee from Southern California Edison, Bill Horstman from Pacific Gas Electric Company, San Francisco, Sina Yusefiano Dam from University at Buffalo, I'm sorry, Sina, Ahmad Ali, and Kushai Akuli, Saif Hussein, Professor Guido Kamata, and Lee Shun from UC San Diego, who took also the notes, so thank you, Lynn. So our team worked on the seismic retrofit schemes. And the first topic that we focused was the retrofit of mid-rise welded steel moment resisting frame structures.
well, the issue identified there was that we have the weak story mechanism. And more specifically, the weak story mechanism drives the demand to column splices that have a potential fracture issue of the partial penetration weld. Also, the shear connections at the gravity beams faced are problematic because of this weak story mechanism, and we may lose our capacity to carry the gravity load. So we identified that there is a need to basically use this opportunity to utilize the shake table in order to assess the dynamic effects in these steel moment resisting frames, and basically try to evaluate retrofit schemes that may utilize different configurations of seismic response modification devices, such as backline strain braces, to control the distribution of the load throughout these vulnerable frames. The second topic was related to the out-of-plane behavior of unreinforced masonry structures. Now, it is, I guess, from research perspective, it is a great opportunity to utilize the multi-directional ground motion capability that we will have with the LH Post 6 in order to combine this lateral ground motion with the vertical ground motions in order to evaluate the seismic capacity of the unreinforced masonry, specifically the effects of the out-of-plane behavior. We discussed about the need to better understand retrofit schemes that utilize FRP in order to provide this additional out-of-plane strength. And also we touched upon to the importance of understanding the effect of infill walls in the global response of building structures. And this is mainly because of the non-ductile response. And how can we address that? What is the detailing that we need to use in order to make sure that we don't have negative effects of these infill walls? The last topic was related to the seismic gap between buildings that have different dynamic characteristics. So sometimes there is an issue with one owner basically has few buildings that are adjacent, but they have different dynamic characteristics, and there are limitations in the seismic gap. Instead of trying to increase the seismic gap, which is impossible, you can tie the buildings together using seismic response modification devices in order to control the forces that are flowing from one system to the other. So one idea was that we could utilize the modular frames that we discussed in order to create, let's say, two buildings with different dynamic characteristics, couple them together in order to see the effect on the dynamic response of these modular frames, but also assess the effect on the non-structural components that may span between these two buildings. And again, this comes back to the idea of utilizing something that the shake table can provide and have repetitive types of tests. Yeah, that's it.
Thank you very much, Georgios. And now session number 5, Anthony Sanchez on bridge structures.
Okay. Can you hear me?
Yep.
All right, good. Let me pull up our PowerPoint. Okay, good. All right, can you see that?
Yep. Yep.
All right, good. All right, so our participants were myself, Anthony Sanchez, Jianyu Cheng, who's a PhD student at UC San Diego, Charlie Sikorsky, who's retired from Caltrans. He used to be the research, one of the research managers working with UC San Diego on research topics. Now he's with ITS at UC Berkeley. And Petros Sideris, assistant professor at Texas A&M, who has been doing research on low damage bridge systems. So our three topics are damage resistant bridge systems, foundation rocking, and different topics related to durability. So topic one, damage resistant design. We were taking this to mean unbonded post-tensioning in columns to reduce damage in plastic hinges and self-center the bridge after an earthquake, and also sliding and rocking joints. And this research has been done. Some research has been done already at UC San Diego, UNR, Texas A&M, University of Washington, and Buffalo. So there's been tests, but there's no clear path on how to implement this into practice. Charlie pointed out that it would be difficult to convince Caltrans and the other DOTs that it could be beneficial, and the benefit has not been quantified yet. It's difficult to do field demonstration projects. If you did a demonstration project, you'd have to wait, it could be decades for an earthquake to happen to test it. So we do need full scale or large scale testing, but this funding may be difficult to obtain. It tends to be pretty expensive, maybe $1 million to $2 million per test. Also, the DOTs and the state bridge engineers are comfortable with the current design methods. They work well. They've been tested. They're in the codes. They've been proof tested during earthquakes, so everyone's comfortable with the current seismic design criteria and the ductility methods. So we think it'll take time to convince the DOTs that we should start doing this testing. I think if we quantified how much money can be saved, that seems like that would be a relatively inexpensive desktop study to show, based on past earthquakes, what the level of damage was to bridges, and if some of these bridges had these damage resistant systems in place, how much money could we have saved in current dollars, and then also quantify other impacts, such as reduced impacts to traffic. For example, if a bridge does not collapse but needs to be torn down and replaced, that's going to have a big impact to traffic. So what is that in terms of impact to the economy? There should be a way to quantify that as well. So I think if we can show the benefits through maybe a low-cost study, rather than doing the trying to do the shake table testing right away, that could lead to more funding for the shake table tests. All right, so that's topic number one. Topic number two is foundation rocking. So this is where either you have a spread footing that is allowed to uplift and rock, or if you need a pile footing, like we have shown here schematically, you build the pile footing that you need, but then you put a reduced size spread footing on top, and that spread footing now can rock on top of the pile cap. So the idea here is that this rocking would occur before the plastic hinge forms. So you can reduce damage to the columns. You would never get a plastic hinge. The system would stay elastic, and the energy is dissipated, and the displacement capacity comes from rocking of the foundation. So this seems like a great approach if if this can be implemented, it seems like it's a low cost. It could actually reduce the cost. For example, if you have a good design methodology to allow spread footings to rock, you can make these spread footings smaller than you otherwise would if you don't allow uplift. So you can reduce the initial capital costs for new bridges, and then also reduce damage and future costs of replacing damaged bridges. So it seems like it's a win-win there. The problem is the current mindset of the industry is to avoid foundation rocking. A lot of the bridge engineers are used to not allowing uplift in footings. They want to make the footings bigger, to put tie downs, kind of a brute force approach to resisting the seismic loads, but it's actually, I believe, going in the wrong direction. We want our bridges to be more flexible, not more stiff. So we need to change that mindset in the industry. And I think we need the research to back it up to show that it is a reliable mechanism for dissipating seismic forces, and that it's ways to assess the stability so that we can be certain that the system is going to be stable, and then come up with some easy to implement design methodologies. So I think there's a big opportunity to do some research there to show how we would design these rocking systems. And then also a big topic of bridge, the bridge industry right now is accelerated bridge construction. So it seems like this would be very well suited to ABC, where you have these precast components. And if you can just take a precast footing and set it down on top of a pile cap without any monolithic connection, that's ideal. So I think we can work with, maybe there's funding available for accelerated bridge construction that we can combine to show these rocking systems. All right, so that was topic number 2. And then topic number 3 had to do with different ways to increase durability in bridges. Some of these may have applications for the high performance outdoor shake table. Some may not have applications. For example, ultra high performance concrete for bridge decks. So the DOTs are spending a lot of money now rehabbing and replacing bridge decks. They get the most wear of any part of the bridge. That's where the live loads are hitting the deck. They're getting impacts, and they get beat up over the years. So if we can come up with more durable bridge decks, that could save a lot of money, reduce maintenance costs. We were talking about doing long-term degradation testings could be for the rocking foundations or for the damage-resistant systems. So where we would test them, build them, test them initially, and then just let them sit and potentially do some aging, some accelerated aging, whether we're spraying them with salt water or putting some kind of live load on them to see how they degrade, and then testing them later. So that would give us a more realistic way to test these bridges in service, right? Because if we build one of these bridge systems, the earthquake's not going to happen immediately. It may happen in 20 years or 50 or 70 years. So we'd like to know that these systems are durable, and that see what they respond like, how they can withstand earthquakes once they've deteriorated or been in service for a long time. And then we're talking about doing live load testing on the shake table. So I know all the discussions have been about doing seismic testing, but maybe there's a way to use the outdoor shake table to simulate live loading and to simulate many cycles of live loading. That could be good for testing the durability of bridge decks, or also testing fatigue in steel members. So that was our topic number 3. There's a picture of the a deck that I showed yesterday. It's a bridge in Stockton that Caltrans is spending millions of dollars fixing this deck every few years. And then potential funding sources. We all decided that NSF is not a good source of funding when it comes to bridges. They defer to FHWA for bridges. So you have FHWA, and then you also have all the state DOTs, especially the ones in seismic regions. So of course, Caltrans, WashDOT, also Alaska DOT, Oregon DOT, Hawaii DOT, and also Idaho and Utah. So there's our summary of the 3 topics.
Thank you very much, Tony.
All right, you're welcome.
And now let's go to Amarnath Kasalanati on earthquake protective systems.
Thank you, Joel. As soon as Sanchez releases, okay, I will share the screen. And, good morning, everyone. It's still morning. Can you see my screen all right, John?
Yes, yes.
Okay, great. Thank you for the opportunity to be in this session. And we had a very good group. We had good representation from academia, manufacturer, a practitioner, and also many people who have used protective systems internationally were there. That is just captured in 8 people you see here. I want to thank Claudio Sepulveda for being the scribe and taking excellent notes. Like all other groups, we were very excited about the large size of the table, as well as the opportunity to apply multi-directional excitation. That is the same for all researchers, but specifically for isolation and energy dissipation fields, as well as rocking columns and such. The ability of this table to reproduce the motion in low frequency or long period content, that is of great importance. Some of the smaller tables cannot do that, so we cannot push the isolated structures quite as much as what they see in the field. So this table provides that opportunity. And also we are excited about the rotational motion and what it means. Of the different things we discussed, we identified 3 topics, and one is the ultimate behavior of devices, as well as structures with the protective devices. And Professor Mosqueda contributed to this, and basically, as the design level motions, that behavior is well understood. But what happens at MCE and with the superstructure yielding, how do these devices interact? And again, this facility with its size and performance capabilities will provide opportunities to test bearings to limits and study what happens to the overall structure and design. The second one is about improving code equations. When you have systems with intersecting lateral systems, you use 100 plus 30% type of equations, which may be unconservative, but 100 plus 100 would be too conservative. So what is the right combination? Those kind of things. Here, it can be combined with what was discussed by the previous breakout groups. Doesn't have to be an isolated or damped, but you can have the damped ones or isolated ones later. For example, in the code, very often you use a combination of hysteretic damping in the superstructure combined with the supplemental damping in the devices. But large structures have not been pushed to the yielding and limits to validate some of those equations. Again, this LH-POS6 will provide opportunities to do that. And then the third one we discussed is the vertical motion and its impact on response. Many of you know of the testing done at eDefense led by Professor Kerry Ryan. It answered many questions, but it also raised several questions about the vertical motion and performance of non-structural components. And it is one data point. There are several papers, but we can add more data by replicating some of those on LH-POS6 and understanding the vertical motions and its impact. So those are broadly what we discussed, condensed into 3 topics. As for the funding sources, the usual suspects are there, NHS, FEMA, and so on, but California resiliency is talked about a bit. Perhaps we are not taking advantage of it as much as we could, or we should be more involved. That is one that is identified. Again, another usual suspect is any high-tech company that have a lot of data centers, talking to them about isolating, damping their structures. But more importantly, a representative from Taylor Devices was in the discussion and has kindly offered to provide dampers. Again, depending on a lot of things working out, size and type of experiments, but that was one thing. And also reaching isolation system manufacturers. The previous large-scale tests, they were very large combined efforts with manufacturers contributing. They will play a key role in making some of these tests happen. Electrical systems could benefit from this research, so that is another source we identified. And then taking advantage of that test bed that Joel mentioned yesterday about reconfigurable, perhaps go to yield and replace some things, and how do we take advantage of that? So that's another one. Basically, the concluding thought is, the SRMD test machine in San Diego that's been in use for about 20 years, its work, it had made from research into practice and into code with lambda factors or bounded design and so on for isolation and damping. The hope of this group is LH-POS6 will do the same for system level performance of structures using protective devices. And again, I thank all the participants in this group. Joel, back to you.
Thank you very much, Amarnath. And now let's go to number 7 with Jorge Meneses on geostructures.
Okay. I'm going to select, I'm going to share my screen. All right. So this is a breakout session on geohazards. My name is Jorge Meneses, and I serve as the moderator. Maitreya Kurumbati from UCSD served as the scribe. This is the list of the participants. Myself, Maitreya the scribe, Bill Black with Mead and Hunt, Ramin Motamed with the University of Nevada, Reno, Teresa Richards, UCSD, and Sia Safir Kleinfelder. Initially, what we did is we did a kind of brainstorm just to identify some potential research areas or topics. So first of all, I would like to emphasize that in the field of geotechnical earthquake engineering is very, very important large-scale testing. In the past, traditionally, has been in the within physical modeling, small-scale testing has been performed. 1G small scale testing, and also centrifuge testing. However, there are some, of course, advantages, but also there are some disadvantages doing this small scale testing. We can capture important information doing this type of testing, but also at the same time, when we perform large-scale testing, as we can do here using the LH Post-6 facilities, either we can have a better picture of the issue that we want to identify. We are going to discuss something about this later when we identify some issues, but I think that this is the very important thing, at least in geotechnical earthquake engineering, the large-scale testing component. Possible research areas study the behavior of piles, foundations in general, pipes in saturated sand under earthquake forces, behavior of shallow foundations in liquefiable soils. Large-scale testing can complement existing available centrifuge testing in this area. Performance design of retaining structures. Yesterday, Cici Nicolau did a very, very important presentation about this topic. And I think this is something that has to be pursued because there are still many things that we need to investigate and evaluate for appropriate characterization of the distribution of the seismic lateral earth forces on retaining structures. Also, another topic that we discussed is input motions, how the input motions are used in this facility, the importance, for example, of near source versus a far source, the importance of short duration versus long durations, subduction versus shallow crustal, etc. Fault rupture, of course, is something very important that Craig described yesterday. And also another topic is, for example, things like interaction of concrete dams with reservoir water. Each one has a different frequency of vibration, and this interaction could be something interesting also to evaluate. So we selected 3 topics based on this discussion. Number 1 is, in general, behavior of foundations, shallow and deep, pipes in saturated sand under earthquake forces. Basically, we're interested when, for example, during the shaking, during the ground motion, soil liquefies, right? We are interested in effects of liquefaction and the induced lateral spread on foundations and also pipes. When we are talking about this type of elements, of course, we are talking basically about, for example, port facilities, harbor facilities, and also we are concerned that in the future, probably in the next 50 years, we have to address, and we have to address from now, experimentally also, the effects of climate change. Like, for example, the sea level rise will contribute to the increase of coastal areas subjected to liquefaction and lateral spread. And this effect has been needs to be studied using this large scale testing. So this is something that this facility will contribute a lot evaluating these effects. Another thing that was discussed yesterday, presented by Cici, and we would like to see this pursued, is a study evaluation of performance and design of retaining structure. In the field, in the literature, we see there will be some information about small scale testing, physical testing, centrifuge testing, but there is not much information about retaining structures. So this is something that we believe will contribute a lot more to understand better the behavior of these structures, depending upon the type of the backfill, depending upon the type of the wall, restrained versus unrestrained. All these variables need to be investigated. And we believe that there is not enough experimental studies. And we think that large scale will complement current studies using the centrifuge. This is something that is needed urgent, especially in the practice. Another topic is about input motions. So especially, when we are dealing with non-linear time history analysis of structures and their performance-based design. Is needed to develop time histories. There is still some many aspects to cover. It's not only from the point of view of engineering seismologies, the study of the ground motion per self, but also at the same time it's important to see how certain characteristics of ground motions affect the response of structures, affect the response of the models that are tested under this facility. So what are the criteria to use input motions, how they are developed, how they are selected? Are they considering near source effects? For example, in near source effect, there are certain characteristics, for example, the poles, how the poles will affect the presence or not of these poles will affect the response of a model sitting on these facilities. So this is something that I think needs more discussion and also needs to be investigated, how this aspect of testing is addressed depending upon, of course, the testing that is being done. So also we discussed some potential funding sources, of course, NSF, Caltrans, PIR, Department of Neighboring States. There are some that are willing to support this type of studies, testing, probably industry partnership with LADWP or some energy companies. Ports, we believe that could be very interested also in this topic, especially with the sea level rise. Port of LA, Port of Long Beach, California Earthquake Authority, probably other federal level agencies such as the NRC, the Department of Energy. I think this is basically the summary of the three topics that we are somehow that we discussed and we are suggesting for future for consideration under geostructures. Thank you, Joel.
Thank you very much, Jorge. And the next one, number 8, Lifeline Utilities by Craig Davis and Elide Pantoli. I don't know who will present. I think Craig, yes.
Yes, I will present. Can you see my screen?
Yes.
Okay. Yeah, so the breakout topic is lifelines. I am the moderator, and Ilde Pantolini, Pantoli, sorry, I mispronounced that, from UC San Diego. We could skip these slides that was there from the description. Our participants were, excuse me for not necessarily getting all your names correctly, but Boris Jeremic from UC Davis, Ming Wang from UC San Diego, Soji Wu from EMD International, Christian Fausto, a master's student and works for Southern California Edison, Christy Nicolau from WSP, Gloria Ferroni from UCSD. Some of these had to come and go at different times during the session, and we had, I think, a good mix of discussion between research and industry. I want to give a quick background slide on the focus of what we're going to present as our topics. So we had targets based on topics that we proposed are based on unique capabilities of the LA Coast 6 that it provides. I don't think that's a well-written statement that I made, but I hope you get the understanding. And to improve the existing design philosophies, for example, recovery-based design rather than damage-resistant design. We're talking about systems here for Lifeline and the ability to provide service, that type of a concept that requires much more in-depth discussion and research on its own. And I'm gonna present some high-level topics that we concluded on, which may be different than earlier discussions. You know, we're not talking about high-strength rebar. We're talking about systems. So the ideas of these details that you've heard in many of the earlier presentations need to still be fleshed out as each project goes forward. So these high-level topics really could be long long-term programs in them into themselves. And each testing scheme requires more detailed descriptions on the material, structural, and geotechnical issues, and so on, targeting specific types of knowledge to be gained by the different tests. So we're going to actually present 4 topics in 2 slides. So I think my 3 minutes start now. The topic 1 is systems testing of lifelines. So this was summarized in my presentation yesterday. So we're going to investigate the interaction, the interconnection of components within stations. For example, electric power substations are commonly used, but there's treatment systems, treatment plants, and water and wastewater. There's the refineries and many other types of components related to all these different lifeline systems that we're talking about. So it's a general topic. We're trying to give a vision of what it is. They all interconnect, right? So this big table gives us an opportunity to either do full-scale or potentially scale models of all these different components and how they interconnect. And instead of looking at each one separately, they interact. So we're able to look at that. And then from that, we can start looking deeper into the fragilities of each of these components and the different types of designs that you might have. Just for each of these components, there's many ways of designing them, right? So you take ATC 58, I think that's the right number, on fragilities of buildings. And they began to focus on different types of structural types, different structural types. And so you could think about that for transformers. There's different types of transformers and the bushing, and then how they're connecting to other types of structures. There's different ways of running the lines. There's different types of these alternate structures and how they all interact. And then there's layouts within these facilities, right? So you actually have an infinite number of possibilities, but you could actually start narrowing these down to very common types of layouts and very common types of materials and designs within each of these components and how they all interact. So then topic 2, tall structures with 6 degrees of freedom being tested. So lifelines have many unique tall structures. Some examples are the wind turbines, outlet towers, smokestacks. The list goes on and on and on. So think of these tall structures. Now, small rotations at the base make a big difference. We saw that in a presentation yesterday. I forgot exactly who it was, but I think they referenced one of my PhD advisors, Professor Kukunik from USC, in one of his research studies showing how that makes a difference. So not only that, but the multi-directional shaking makes a big difference. I made reference to recording in the LA 80-foot high or 100-foot high, I think it was LA Reservoir Outlet Tower, that swung, I think, 10 times, and 1G recorded in both directions. So that means it's swinging in a circle, right? That's a very big difference in stresses in the members than when you're shaking at 2D. So you might think about going back, first and foremost, to this wind turbine, testing that same wind turbine again with these multiple degrees of freedom to begin to understand how these multiple degrees of freedom actually do make a difference. Start documenting that, and then create a program where you're systematically testing these different outlet towers with different materials and retrofit schemes and so on. Topic 3 is long linear above ground structures. Yesterday I gave a presentation on pipelines. But there's also transmission cables, and when they're shaking and they swing and they can hit each other and create faults. And so there's all kinds of different long linear types of structures. Here we're talking about above ground. I get to below ground in the next one. So we need to investigate the differential behavior of the foundations from wave propagation and different soil conditions at each site, and how the supporting affect the supported components behave, the wires, the pipelines, the concrete slabs, and so on, with out-of-phase motions between these different supports. And from this, and actually it applies to some of the earlier parts, I think topic 1, we should think about extending the size of the table. So we're not necessarily talking about large or massive structures, but maybe we could use the capacity of the table to allow for cantilevering out to test more in this area for topic 1, right? When we're looking at systems and for the lengths of these long linear structures. So we challenge people, researchers, to think about that. And then topic 4 is below ground structures or underground structures. There's many unique and complicated structures, box type structures and pipe type structures or cable type. I talked about it as type. And so I referred to presentations yesterday, but I itemized some topics here. For sake of time, I talked about these in my presentation yesterday, so there's more detail in there. But these are the 4 types of structures or 4 types of programs, actually, that we recommend this to be taken on. So Joel, these could be very long, decades-long programs that get integrated into the testing. Potential funding sources would be maybe combined NIST, NSF, and industry. The industry may provide less funding, but more value in kind resources, material, engineering, and input from a practical industry perspective. Then there's other federal agencies, EPA, DOE, and so on. So think about, communications. They have many different types of federal agencies governing them, and state agencies. So these are types of things that could be addressed for funding. And I'm going to leave it there for the next.
Yeah, thank you very much, Craig. Thank you very much.
Sure.
Number 9, Professor Tara Hutchinson, talk about non-structural components and systems.
Okay, great. Just get the screen shared. Can you see the slides okay?
Yes.
Okay, thank you. Myself and Michael Morano, one of our PhD students, helped moderate and scribe this session. We had a very good discussion. Here are our participants. Robert Belvin from Construction Specialties, coming with an interesting angle of the architectural perspective. Nate Deibler from VMC Group, doing a lot of work on testing and certification of NCSs. Scott Harvey as an academic researcher, looking at equipment isolation and seismic protection, amongst other things. Hossein Mostafai from FM Global, doing a lot of work on earthquake losses and risk, brings a very unique perspective to the issue of the overarching issue of NCSs. And Derek Watkins, one of our former PhD students, has a rich career in looking at issues of qualification of equipment, piping, bracing, and the like. So we had 7 of us in this discussion. We discussed 6 topics, and in the interest of time, we were requested, of course, to bubble up the top 3. And the way we organized these was, what the general topic was, what some of the issues we each could bring to the table relative to that topic, what some possible solutions might be with LH Post 6 to addressing and contributing to advancing this topic, and there's definitely some impediments. In the interest of time, I'll just point out the topic and then offer up what our thoughts were on what the possible solutions were with the exciting advancements of LH Post 6. So the first topic was seismic force estimates for NCSs. In a global sense, our consensus was the general expression of FSP just doesn't work well across the board. Perhaps it works for some, not for others, and there's a variety of issues I think one could bring to bear to recognize that. However, with LH Post and possibly the use of a universal base frame, for example, or the modular test building, that could facilitate experiments to study the FSP distribution. That was one option. Another option might be, and of course there could be a long laundry list of structural configurations to study this issue, but fixing connections to the reaction mass and moving with moving and or flexible connections to LH Post or the universal base frame, that could also provide an opportunity to report seismic forces for semi-flexible connections. The second topic, I'm not sure that if there's an impediment in your screen for the top of the slide, sorry about that. Second topic was interactions between NCSs and interactions between the NCSs and the primary structure. So they're separate topics, but similar problematic and uncertain response issues that come to bear. We know that they're not always isolated components. We ask the question, are they synergistic or are they counterproductive? I think Professor Scott Harvey had some really interesting points there. Could they be aggravated? And if not, could we utilize flexible connections? And if so, could we utilize flexible connections? So some possible solutions to study with LH post 6. One, I think, healthy discussion was the idea of performing hybrid testing with the shake table, with the newly configured shake table, newly upgraded table. The computer model in that case would be the building. That would allow the researcher to easily modify the computer model to account for different buildings and configurations, whereas the NCS as a specimen would be the physical payload. And that would allow multiple, in fact, NCSs to be mounted and assembled and or arrayed onto LH post 6. The other natural thing, and I think the modular testbed has been sort of strategically designed to help out with collecting information in this regard, was to strategically lay out a program in a systematic fashion and use that 3-story building to deliver those interactions. The third topic was the responsive contents. The data that's out there has largely been limited to residential contents, shelving, really small contents. And Hossein really brought this up as an impediment in their work from the insurer's point of view. The reality is the data is lacking for large warehouse type of contents, especially those that are mounted, they're elevated. Pharmaceutical, mechanical equipment, manufacturing storage facilities, wine storage facilities were some of the ones brought up. The limitation there is that damage vulnerability functions are really not well developed because the experimental data as a basis to understand the damage is lacking. So possible solutions with LH posts, a natural opportunity to test at full-scale storage racks under multiple degrees of freedom input excitation. And then the parallel to that, or the follow-on, might be to investigate protective systems that could be utilized in this scenario to protect these large and heavy contents, often mounted on either single point or multiple point storage racks. So I tried to give us a little time back. Hope that was useful. I want to thank the colleagues who joined that session.
Thank you very much, Tara. And the last one, seismic qualification of equipment, Derek Watkins.
Hello. Let me share my screen.
Derek was multitasking, by the way.
Yeah.
We claimed him in our session.
Moderated one session, finished early, and I jumped into the other one. All right, so our topic was seismic certification of equipment. The participants are listed here. We had a small group, but a nice diversity from university to test lab to utilities to people who do seismic certification as consultants. Our priority research needs, topic 1 is commercial testing needs. We believe because the size and payload capacity of the LH post that a significant amount of commercial testing could be done there, potentially up to 2-3 months a year of testing for very large equipment that's currently being tested either at Berkeley or at the Army Corps of Engineers lab. To do that, the lab will need to have the certain accreditations and quality assurance status that it needs. It may already have some, may need to expand it. And then topic 3 was research needs. I guess on the industry commercial testing side, there's a variety of test standards that the lab would have to be certified to, IEEE 693, 344, and AC 156. We would need to know for different payloads, especially heavy equipment, what the spectral capabilities of the table are on the low frequency end and on the high frequency end. Some equipment, the standard for AC-156 is to test up to 3.2 Gs, 5% damped spectral acceleration. But for specific projects in 693 and nuclear, it could be higher, as much as 5 or 6 Gs, and then some narrow banded frequencies even up to 10, 12 Gs. The equipment, heavy equipment, is not going to be a problem for the table since it's designed to take so much payload. The most important thing would be that cost and schedule at this lab are similar to or competitive with other commercial labs that can test heavy equipment. The table would have to be outfitted with a sort of special platen on top of the platen that's sacrificial that you could bolt and weld to. And then instrumentation requirements. Some tests require actual direct displacement measurement at the top of the equipment, and then load and strain in the anchorage of the equipment. The accreditation that you would need on the commercial side is IAS accreditation or ISO 17025, which I believe the lab already has. Just needs to list AC-156 and IEEE 693 on the certificate. And then if the lab is interested in doing nuclear testing, it would have to be a NQA1 ASME quality assurance program. So I think that's a majority of what I can see the table being used for, and funding for that is by the individual manufacturers who are looking to achieve a seismic certification. On the research side, we think that because of the size of the platen and the payload capacity, there's some heavy transformers that have bushing failures in substation equipment that could be investigated on the table. And then another thing for substation components, as well as other interconnected components, is this need to put maybe 2 or 3 pieces of equipment on the table interconnected, especially substation equipment, and see how the interconnection causing load back into the equipment works. And then we don't know the current status of suspended ceiling testing, but if the table had a wall-mounted frame as well as like a elevated ceiling-mounted test frame, then you could do suspended ceiling testing. So that was it.
Great, thank you very much, Eric.